to the topic here, determination of molecular shapes. Determination of molecular shape. This is actually drafted out of structure and bonding. Alright, now every shape that you see, or rather every molecule that you see possesses a shape. Every molecule, whether it's a molecule of water, or it's a molecule of an ethane, or it's a molecule of sulfur dioxide, every molecule that you come across possesses a shape. But how do we determine the shapes of this molecule? Some of these shapes are classified as being linear. Some of them are classified as being, tetrahedral. Some of them are bent. Some of them are seashore shapes. Okay, so some of them are even trigonal bipyramidal. Some of them are trigonal pyramidal, and different type of shapes are always being identified with different type of molecules. Now, the essence of this art class is to see how we can be able to determine the shapes of this molecule. Now, do you know that every molecule that you come by, most all molecules you come by possesses what you call a central metal atom. Now, a central metal atom is simply an atom that bonds itself with other atoms. So you can have 1, 2, or 3, or even more than that, several different atoms that bond themselves to a central metal atom. Now, this central metal atom controls a whole lot as far as shape of molecule are concerned. So if you take a look at this diagram, the X that is written here is the central metal atom. Now, with this central atom that you have here, it bonds itself, okay? It bonds itself with other atoms. And this bonding that you see from the central atom with other atoms around it is usually a covalent bond. So it means that the central metal atom, or the central atom as the case may be, because in some cases it may not be a metal, but the central atom as the case may be, usually bonds itself with other atoms through covalent bonding. Now, it bonds itself with other atoms through what we call electron pairs. So it means that there exists electron pair, or electron pairs as the case may be, in every molecule that you see. And this electron pairing is because of the covalent bonding that exists between the central atom and the other atoms that surrounds it. Now, these very electron pairs that you see here are always known to either be bonding pairs or they are lone pairs. They are bonding pairs or they are lone pairs. Now, when they are bonding pairs, it means that these particular electron pairs, if they are two, they are a pair already. So these particular electron pairs that you have here will always do what? Or will have always done what? Bonded themselves with the central metal atom and another atom around the central metal atom. Then you can classify such a bonding as such a pair as a bonding pair. But where the pair of electron does not bond itself with any other atom around the central atom, but rather bond itself to the central atom alone, it is now a lone pair. Now, both the lone pair and the bonded pair do so much work in the determination of molecular shapes. So when we say that we are determining molecular shape, it means that those particular two identities that plays a major role in the determination of shape of molecule is the central atom and the electron pairs. So the electron pairs around the central atom plays a significant role in the determination of molecular shapes. You must take that into consideration. And we say that whether they are lone pair or they are bonded pair, they still play a role in the determination of molecular shapes. Now, remember that these very bonded and lone pair electrons, as we say, play a role. But the lone pair electron appears to play a major role or more role than the bonding pair in this determination. Okay, now this is because the lone pair electrons usually repel themselves afar. Electron pairs around the central atom are always negatively charged. So they have a tendency of doing what? Of setting themselves far away from themselves in order to minimize what? To minimize repulsion. And usually the lone pair electrons, that is the ones that are bonded only to the central atom but not bonded to any other atom away from them, those lone pair electrons are always having a greater repulsion. And because they possess a greater repulsion, what happens? They do what? They try their best to minimize that repulsion. In that case, they have a longer stretching, and that stretching affects both the bond angle, affects both the bond length and the structure. Because of that, it determines more the structure or the geometry of what, or the shape of molecules. Now I want us to know that around the central atom there is what you can call electron cloud, electron charge cloud. Okay, around the central atom there is what you can call electron charge cloud, and usually the electron charge cloud is simply the probability of finding electron pair around what? Around the central atom. So when you are saying electron charge cloud, what you mean is that particular region around the central atom where you can probably find electron pair. And usually the electron charge cloud is dominated by negatively charged electrons. And that dominance does not matter whether the electrons are actually lone pair or they are what? They are bonded pair. There might also be a mixed pair. So usually this particular electron charge cloud also plays a serious role, a significant role in the determination of molecular shapes. Because as long as it possesses or houses both lone pair electrons and bonded pair electron, it means that it also plays a serious role in the determination of what? Of molecular shapes. Now, do you know that the major item that you can be able to use to determine molecular shapes is the valence shell electron repulsion theory? If you have heard that before. So we have the valence shell electron pair repulsion theory. It's always written in this form, the valence shell electron pair repulsion theory. What that means is, this theory simply says that electrons will always, the electron pairs, okay, whether bonded or lone, will always keep themselves apart, far away, in order to minimize what? Repulsion. And that usually it is this electron pair that keep themselves apart because of what? Because of the forces, the repulsive forces that are created around them, that will always allow for what? For shapes of molecule to determine. And usually these very shapes of molecule will determine from the valence electrons. So it means that through the valence shell electron pair repulsion theory, we can be able to determine the shape of molecule, provided we understand the number of electrons that are in the valence shell of this central metal atom, or this central atom. Okay, so the valence shell electron pair repulsion theory is the major theory that explains the fact that you can possibly be able to determine the shape of molecules when you understand when you are able to count the number of electrons or identify the number of electrons at the valence shell, that is the outermost shell of this particular central atom. So it will be nice if you take a look on your own, you try to look at what the valence shell electron pair repulsion theory is all about. But briefly, I've said it. Now, let us take a look on how we can be able to determine shapes of molecule from the valence shell electron pair repulsion theory. How do we determine these shapes of molecule? Now, number one, for you to determine a shape of a particular molecule, number one, you must be able to identify what? Identify the central atom. When you are given a particular molecule, for example, somebody gives you, let's say somebody gives you beryllium fluoride, okay? If somebody gives you beryllium difluoride, and you are expected to determine the shape of beryllium trifluoride, you must first identify that particular item among the two that is a central atom, that you can now bond the other atoms to it. And of course, you will know that from here, beryllium will definitely be the central atom. Now, if you have been able to identify the central atom, which from this diagram, this is the central atom. If you are able to identify the central atom, now it is now left for you to know the number of electrons, the number of valence electrons at the outermost shell of this particular central atom. Number one, I said identify the central atom. Number two, you must be able to identify the number of electrons at the valence shell. Take for example, if you were dealing with sodium, you know that sodium is 11 electrons. So 1s2, 2s2, 2p6, 3s1. That means that for sodium, which perhaps will have been the central atom in the determination of maybe the shape of sodium chloride, for example. Alright, so if sodium was supposed to now be the central atom, you have identified it. The next step is for you to know the number of valence electrons at the outer shell of sodium as a central atom. And it means that for sodium, it is 1. It is 1 electron that is a valence electron. Remember that this particular shape of molecule is always by covalent bonding. And covalent bonding explains simply a shear pair of electrons where the central atom donates an electron, and then the other surrounding atoms will donate also an electron. Okay, now that is number 2. You are able now to identify what the number of electrons at the number of valence electrons at the outer shell, okay, of this particular central. Now the next thing for you to do is to make your own contribution. Your own here, I mean the central atom. Now the central atom is going to what? Contribute 1 electron, not a pair, to each of the atoms that are actually bonding to it. Now here you see 1, 2, 3, 4, 5, 6. It means that we have 6 different atoms that are bonded to the central atom. After identifying the central atom, going again into identifying the number of electrons that are at the outermost shell as valence electron, the next thing we do is to do what? Is to contribute. It's for the valence electron, it's for the central atom to contribute what? 1 electron each for the atoms that are actually bonding to it, to form a shear pair, to form 2, 2 as it is. So it means that here you have 1 electron coming from here and 1 electron coming from the other atom. The same thing here. So you now have a shear pair. Now when you are able to have a shear pair, the next thing for you to do is to do what? Is to count all the electrons that constitute that particular molecule, irrespective of whether they are lone pair or they are what? They are bonded pair. So for here, we'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 total electrons that are contributed by the various atoms that bonded themselves, okay, to the central atom. So you divide it by what? By 2. You have 6. That is why you are having 1, 2, 3, 4, 5, 6 pairs of electrons. With the 6 pairs of electrons, you can now sit down and identify among the 6 pairs which of them is a lone pair and which of them is a bonded pair. Bear in mind the fact that lone pair are having greater stretching. They have a greater distance away from themselves, so they contributed higher to what? To the shape of the molecule. And if we take this for an instance, it means that this one is bonded, this one is bonded, This is bonded, this is bonded. These two are not bonded. So we have one pair, two pair. So two pairs of electrons here are not bonded. That's why we said for this particular compound, there are two lone pair. And with the presence of two lone pair, we can classify the shape of this molecule to be square planar. Did you see how very simple it is for you to determine the shape of a molecule? Now, if we understand this, let us see how we can be able to determine the shape of a few other molecules before we end this class. So I'm going to remove this. I'm going to remove this and give us the opportunity to look at a few of them. Now, if we are asked to determine the shape of a molecule, for example, a molecule like, let's say a molecule like beryllium dichloride. If we are asked to determine the shape of beryllium trichloride, first from our description of the steps involved for us to determine shape of molecule, number one is to determine what? The central atom. And in this beryllium, this is the central atom. While this chlorine is what? Or the chloride is what? Are the other atoms that will form what? That will form the electron pair cloud around the central atom. So we are going to write beryllium, and then there are two atoms of chlorine bonded to what? To beryllium. So we attach chlorine here, we attach chlorine here. In this case, you have two chlorine atoms that are bonded. And since two chlorine atoms are bonded to beryllium, okay, it means that the shape of this molecule is linear. So it's linear shape. You can have this if you want to. This is showing you the other atoms that are of chlorine that are bonded. Okay, now this shape is a linear shape. The bond angle from here to here is 180 degrees. And this is because there are a lot of stretching, okay, from this bonded pair of electrons, such that it stretches what? The bond length and bond angle, and give an angle of 180. You can also have another, let's say boron trifluoride. Okay, boron trifluoride. You have boron trifluoride. Here it means that you identify the major shape, okay, the major shape, and then the major atom, the central atom here is what? Is boron. So we have boron. Now there are three fluoride atoms that are attached. Now in this way, you are going to have fluorine atom, okay, attached that way. You're going to have another fluorine atom and another fluorine atom. Now if you follow the steps in which you can use to determine the shape of a molecule from the valence shell electron pair repulsion theory, as I explained earlier, it'll be easier for you to be able to place the various atoms around the central atom. So with this is bonded. These are bonded atoms. Now, since these are bonded atoms, there is what? A bond angle of about 120 degrees in this. Now, this shape, if you take a look at this shape, this is a planar shape. It looks like it's lying flat, okay, on a table. This is a planar shape. So you can simply describe this as a diagonal planar. A diagonal planar shape, because it looks like the shape is actually lying flat. So it is what? A diagonal what? Planar shape. You can also look at an Another one, let's take a look at something like methane. Let's look at methane, for example. If you look at methane, CH4, you will notice that methane is having hydrogen atom bonded to carbon. With 4 hydrogen atom bonded to carbon, it shows that carbon is already tetrahedral, okay, from your carbon classes, okay, so hydrocarbon classes. So carbon is always what, tetrahedral, and has a maximum bonding of 4 different atoms. So you see that we have C, which is a central atom, with these ones as ligands, so to say, that are bonded. So in this case you have a bond of hydrogen. Okay, so you also have a bond of another hydrogen. You also have a bond of another hydrogen, and then you have a bond of hydrogen here. If you take a look at this particular structure of methane, the bond angle is about 109.5 degrees. Okay, and this shape is always known to be tetrahedral. So it has a tetrahedral structure. All right, and we can go on and on and on. You can look at a shape like ammonia. You can also look at a shape like ammonia. Okay, ammonia is NH3, like ammonia. Ammonia has N as the central atom with 3 hydrogen atoms. Okay, so it has a hydrogen atom here. It also has another hydrogen atom here. And then it has a hydrogen atom here. Now it has a pair of a non-pair of electron. Okay, it has a pair of lone pair electron. So you can see that it has a bond angle here of about 107 degrees. Now the shape of this particular ammonia, okay, if the shape is properly drawn, okay, you'll see that this shape is a trigonal. It's a trigonal pyramidal. It's a trigonal pyramidal shape. Okay, so you can go on and look at the one that is linear, because even if you said it was carbon dioxide has 2, just like you have beryllium dichloride has 2, so you have oxygen to double bond to carbon to double bond to oxygen. Okay, you have that. Okay, and this structure is also 180 degrees, and this is also linear. Okay, so you can go on and look at other shapes of other molecules. But the most important thing for you to know here is that you must understand the various steps through the valence shell electron pair repulsion theory in order to be able to use the Lewis structure to first identify the various lone pairs, the various bonding pairs across a particular molecule, and then be able to now do what? To now determine the shape from especially the lone pair electrons. Now let me drop an assignment for you. You are going to do an assignment. You are going to, on your own, determine. Okay, so you determine the Lewis structure, and shape of the following. Okay, so you determine the Lewis structure, and the shape of the following molecules. Okay, let me say so, of the following molecules. Okay, so 1, you have phosphorus. You have phosphorus trichloride. 2, you have nitrogen oxofluoride. 3, you have phosphorus pentafluoride. 4, you have water. And 5, you have xenon tetrafluoride. Okay, so you have this. You will go and try this on your own. You can do it as an assignment. You can drop it on the comment section of both the WhatsApp and the comment section of the YouTube section if you wish to. But you have to do this assignment for us to know if you understood this lecture very well. It's a pleasure having you around this class today, and I'm glad that we're able to do justice to the determination of molecular shapes. Don't forget to share. Don't forget to also comment, to like as well. Now, when you share this class, you are going to tell those who are sharing this class to in groups to do what? To subscribe. When you subscribe, whenever lectures like this come up, they pop on your screen and you'll be part of it. Now, in the YouTube is Dr. B Science Classes. Dr. B Science Classes in your YouTube. Okay, in your YouTube is Dr. B Science Classes. Even on Facebook is Dr. B Science Classes. When you share on, you need share